Okay, so welcome, and JC, you are welcome to start with the submodeling and topology optimization, session 3 of the FEA series for us.
Okay, thanks, Laura. So let me just share my camera at the beginning now. So hi everyone, and welcome on this 3-week journey that we've had together so far. I hope that I can maintain your expectations, because the first 2 webinars in the series were done very well. So I hope that you're not expecting the same quality today, but I'll do my best. Yeah, so I think that I've had the pleasure of dealing with a couple of you in the past. So welcome everyone. And yeah, today we're going to do some fun FEA modeling, and I'm going to show you some useful tools and tricks, and we're going to focus predominantly on the workflow, because this is more of a little bit more abstract, more fun for us to investigate with the topology optimization and the submodeling. And yeah, if at the end you decide that you want to take this design, you are welcome to have it. It's going to be quite expensive to make, but I think it looks quite interesting at the end. Okay, so I'm going to stop sharing my camera, and I'm going to start sharing my screen with you. I've got a couple slides that I'd like to just go through, and then we can get going with the live demo. Okay, so let me just share my screen quickly, and I hope that everyone can see my screen. Okay, so again, welcome to the Ansys FEA series that we've done with QFinSoft. And today we're going to be looking at some of the final touches on closing up this webinar series. So our agenda for today is going to be, we're going to just quickly have a quick overview on the previous webinars that we've gone through. Then we're going to look at what our next step is going forward, because now we've analyzed our design, and now we can maybe become a little bit more creative and look at exactly what we would like to change about the design, or what we'd like to refine about our design. Then, as Laura mentioned, we're going to look at topology optimization. We're going to do the very basics of topology optimization, but I'll highlight some key features that you can investigate yourself, or the other topology optimization settings and so on. And then we're going to look at submodeling, which is one of my favorite topics. Can be a little bit more challenging sometimes. And the thing is, with both of these operations, or these tools that we have at our disposal, they are a little bit iterative. So often we're going to do one thing, and we're going to have to go back and change a couple things. So today we're just going to go through that very first iteration to set you in the right direction, show you the tips and tricks, and then hopefully you guys can take advantage of these tools at your disposal. Okay, so starting off where we left off in the previous webinar that Jean took you through, is we have the chair that we went and we investigated, and we got some interesting results where we looked at different types of modeling and how we can incorporate not only solids and shells, but we could go and put beams into this analysis. So we've got a really multi-layered approach to getting different accuracies within different regions. So we could see that for those of us that are chronic rockers, we're going to wear out our chair a little bit quicker, just from that harmonic simulation that we had a look at. And then we also noticed that right here at the base, where the feet are actually attached to the chair, we're getting quite high stresses within that region. So that's maybe a region that if we were designing an office chair, we might want to go and investigate this a little bit further. But after we've looked at our initial investigation, you might think, what's next? So there's one application for our office chairs, but another thing is we can look at improving our design for whatever it is that we'd like to use our office chairs for in the future. So although this is not recommended, this could be one of the cases that you investigate in the future. So the things that I'm going to focus on today, as far as our office chair simulations are involved, is our topology optimization and our submodeling. So these two are going to be coupled together in the analysis. Effectively, all that we're going to be doing is for the topology optimization, we're starting off with our base case. We take in that base case and we're going to go and try and reduce the weight while maintaining the strength of the base of the chair in this case. And you can see this is basically the flow. So we'll start off with our solid structure and we'll iterate it till we get something that's really nice and clean. Slightly more complicated geometry, but with additive manufacturing nowadays, this could be a more important topic in the future. And there's definitely a case to be made for this because Ansys itself has a complete additive manufacturing workflow that's been developed for you. So if you decide that you are going to get into the additive manufacturing game, there are workflows dedicated to this, incorporating the topology optimization. But we're not going to look at this today because that's a whole nother beast on its own. So we're just going to stop at the end of our topology optimization, look at a little bit of the workflow for the topology optimization and what we need to consider. And then the other thing we're going to look at is submodeling. So our submodeling is basically where we actually just go and take a full model. We run what the deformations and displacements and strains and everything will be on a full model. In this case, it will be, for example, shells. And then we'll look how we could transfer that into a more detailed model of a specific area. So this is a tool that I often like to use. It's particularly useful for if you're looking at welded geometry or just an area of high stress concentration or any sort of area of interest. So we take advantage of our computational speed and we have a very coarse model and then we refine it to a fine model. So that's effectively what we are doing. So when we are looking at our topology optimization, the typical workflow is something like this. So we'll start off with our initial base case simulation. So that base case simulation will serve as the starting point. Then using the results from that base case simulation, we can set some objective for our optimization study and some criteria for the optimization study. And we'll look at what the different options are for that. Then after we've run our optimization study, there is always going to be some CAD cleanup, geometry cleanup at the end. And then I'm going to take you back to SpaceClaim and show you some really useful tools for actually doing this. And then at the end is actually the validation. So we'll go and look at validating that geometry. So when we actually look at this within our workbench interface, this is something that we're going to see. So we're going to have our geometry and we're going to start off with the static structural, and you can see how we transfer that model into our topology optimization. And then I like to, the reason that I excluded the automatic validation from here is because I like to do things a little bit more manual, because then I've got absolute control over all the things that I would like to change and manipulate. So that's basically what we'll be showing. I'd like to show my workflow. There are other workflows available, but I think that I've spent a little bit of time now playing around with this, and I think that my workflow, I personally like it, so hopefully it'll be useful to you, even if you choose to go a different direction. And then we'll look at submodeling. So over here, we could see basically, just for an example, what the submodeling involves is we take our global course model, we go and we do our analysis on this model over here. We identify, for example, a high stress region, as you can see at the top right, and then we could decide, okay, we'd actually like to go and investigate that region further. So then we go back into geometry, go and cut it out, and then we go and refine our model within that region over there. So submodeling can be a little bit tricky sometimes, but that's why you have us to give you support on fixing up your models, addressing some of the limitations, and so on. And then at the end, we have our submodeling workflow. So this is typically what we would see for our submodeling workflow. So we'll start off with our initial simulation. So that's going to be our global model. Then we have to go and do our submodel geometry preparation. So that's cutting out the region, making it ready for simulation. Then setup, I included setup as a separate step within this workflow, just because it is a little bit more tricky, and you have to get 1 or 2 steps right. And then at the end, we're going to look at just solving our submodel and addressing some of the issues with that. And then if we just go and look at our workflow and what it looks like within the Workbench environment, this is typically what we'll see. We're just going to drag our solution onto the setup, and then we're going to have different geometries and models, unlike in the previous example where the topology optimization, everything was shared. In this case, it will not be. Okay, so I think I've spent enough time going through some slides now. So I'm going to just stop sharing my screen. And then I'm going to share my other screen so that we can go through the actual demonstration. Okay, so I just have 2 screens here, so it's set up a little bit differently. Okay, so let me minimize all of this stuff and let's start off with the project. So in the previous case, we ended off with our entire solved geometry. And I'm just going to start off where we ended off the last time. So we did the static structural, the harmonic, and the modal simulations of the office chair to investigate the performance of the office chair and the operating life and that type of thing. So now I'm going to show you, the first thing that I'd like to show you is how we can go from using those results and incorporating a new geometry for the topology optimization study within our Workbench environments, and how we can do that quite easily. And this might be a trick that not everyone is aware of, and that's why I thought, let me just include as many tips and tricks as I can within the webinar to try and assist you guys in the future. So while this thing is loading, I do have the other models all set up and solved. So a little bit later, after this is probably the longest part of the workflow, is just opening the models every time. While the webinar is going on, I'm also just monitoring the chat. So if there are any questions as I go along, then please feel free to just type them in the chat, and then I can address them for you as the webinar progresses. Okay, I've got a lot of things open, so it's taking a little bit longer than what it normally does. Sorry about that, everyone. Okay, there we go. So this is basically where we left off the last time. So we had our static structural, our modal, and our harmonic response analysis. So the first thing that I would like to do is we're going to not use the previous geometry exactly. So if I just open up mechanical here, previously we used beams in order to model the feet of the chair structure. And with the topology optimization, unfortunately, the beams will not really be of any use to us. You can use topology optimization on shell structures as well, but these beams at the bottom are not going to be of any use to us. So what I need to do is I need to go and eliminate and remove all of this geometry over here. And then typically the way that you'd have to do this is if you go and make changes to the geometry and you go and change the bodies and everything like that, you might have to come back and actually rescope a lot of, as you can see, we've got a lot of connections and contacts and joints and everything like that. And then we've got all of these settings already defined. So one thing that I don't like to do is I do not enjoy having to go and recreate things from the ground up. And often when you have to share work with a colleague, it might not be the most optimal way of doing things to go and recreate everything from the ground up. So what we're going to do is we are going to take that exact setup and we're going to transfer it into a new model that we can actually use for our analysis. So I'm going to start off by duplicating this. So when I duplicate it, it's just going to give us another static structural cell over here. And then what I'm going to do is I'm going to use a global assembly mechanical model. And then the nice thing about that is we can subdivide our model into different sections that we can address within each model. So for example, in this case, I'm going to have this global model, and then I'm going to have a base model also included. So the way that we do this is I come down here to the mechanical model. I'm going to take this and I'm going to drop it over here. And then what we're going to do is, so this is going to be the base. Then over here, we're going to have the chair. And then over here, what we're going to do is we're going to take another mechanical model. I'm just going to drop it over here for now. And then we're going to link them all up. And then we're going to work with a global assembly. So the first thing that I'm going to do is I'm going to go back into this model over here. And I'm just going to go and remove all of the cross sections that we've defined and the beam elements that we defined in the previous demonstration. And just remove those from our analysis. And then we can continue. So the first thing I've got to do is I've just got to come here. Unfortunately, for the topology optimization, we won't be able to use our inertial loads. So we won't be able to use the standard Earth gravity over here. So that means that this point mass isn't going to really be applicable, but we know that it's 125 kilograms. So we're going to just apply force that's equivalent to that. So I need to start off by just saying suppressing that point mass. Then over here about the beams, I'm just going to go and select them all. And then I'm going to go and say suppress body. There we go. So all of those are suppressed. And then something that I know is when we have all these cross sections defined, but we don't have any bodies over there, these can give us a little bit of issues later on. So I'm just going to go and delete all of these cross sections that we have. Okay, so now all of that's gone. And as you could see, all of our joints and our contacts and everything are still within the model. And even better is the mesh is still part of the model. So now I don't want to have to go and remesh this and change all of the settings. So that's why I'm using this global assembly model that we can use later on. So I'm just going to close this and say, cool, I'm happy with everything that's defined over here. It's got the materials and everything already created. Now we're going to go and add in our new base. So I'm going to come to this base model at the bottom, and I'm just going to open up the geometry. So what I'm doing is I'm actually taking at a model level, I'm taking all of these with the mesh, contacts, connections, everything like that, and I'm putting it into one global model over here. And then we can edit each of these individually, and we can make sure that in our global model, we don't go and change something unnecessarily. So what I'm going to do now is I'm just going to go and open up, I think it's this one, the chair topology optimization base. So I've just gone and created a bulk base. So you don't want a predefined area. You want to see what the topology optimization actually gives us out of this process. So what I've got is I've got the imprints of where all of the feet are. And then I've got a solid block that I'm going to use that's going to just be aluminum alloy in this case. And we're going to go and basically eat away at this geometry to go and create an optimized geometry. Okay, so I'm happy with that geometry, so I'm going to just close it. Then we can come into our model. And once we go into the model here, these settings that we apply are only going to be applicable to the base geometry that we have defined over there. So that's something important to take note of. Once we've taken it across, it's not, we can change it if we want to, but I'd suggest that you don't. Rather come back to this model and edit whatever needs to be changed. Okay, so just as to read it in. Okay, so we've got our geometry over here. And then all that I need to come and do is change this assignment for the material, similarly to what we've done in the past, and make that aluminum alloy. So just take notes over here, it is aluminum alloy. But you'll see when we transfer it over to our global model, the assembly model, it's going to be renamed to aluminum alloy 2 because the original model also has an aluminum alloy. So now that's been added to our materials over there. Then what I'm going to do is for the mesh, I want to always turn off my adaptive. I personally do not like that type of meshing strategy. And then I'm just going to make this 10 millimeters all round on this geometry. And then something else that I'd like to show you is I'm just going to go over here and then I'm going to go and create a named selection for this and for this that we can use a little bit later on. So in this, I'm going to go and say create a name selection, and I'm just going to say exclusion region. And you'll see why we use that a little bit later on. So now we've got everything over here. We can mesh this very, very quickly. And here we've got all of our TET elements. So generally for the topology optimization, in this case, I didn't have to go and define anything. It went and defined it for us. But you actually do want to use TET elements for the topology optimization mesh. And the quality of the result that you get out of your topology optimization will be dependent on the mesh that you create. Okay, so we are done with that model. Now, the way that we link all of these up is we're going to take this model, drag it on to that model over there. Then we're going to drag this model onto that model over there. And now we've got our global assembly model over here. Then all that we've got to do is we've got to go and update the upstream component. So it's just going to go and make sure everything's okay between those two models. It won't take very long. And then it will actually show us everything put together within this model over here. So now what I've done is I've eliminated the need to go and recreate any geometry. I've eliminated the need to go and redefine all of my boundary conditions, my name selections, and connections, and everything like that from the original model. And we're just taking it into a new model. So that means we have consistency between these two models, and we are not going to go and mess up anything of our colleagues' work or something like that that they might have sent across to us. So now, just so that we can skip an additional step, I'm just going to come over here to the static structural analysis, drop that on the model over there, and you can see that linked to the model level, and then I'm just going to come and edit this. So this is going to be our new static structural analysis for the topology optimization model. Okay, and as you can see, great, everything looks good as we've brought it in already. So when you go into your geometry, now we've got the chair, so that's the original, and as you can see, it's got the point mass suppressed, for example. And what you can see now is all of these are grayed out, which means that I can't edit them. If you do want to edit it, you can go to read only and change it, but I prefer to not. I'll rather go back and change the original and make sure that in this instance of the model, nothing can go and be edited. And then here, again, we've got our aluminium alloy 2, like I told you, and everything's defined over there. So that's great. We've got the materials automatically brought across. We don't need to go through coordinate systems or anything like that. The one nice thing is now what we can go and define is for the model over here is our contact region. So our original contact regions and connections are under the chair branch over here. Everything else that gets created automatically will be over here under the contact branch. So if we come and look at the contact branch, then you can see over here, it went and it picked up the contact between the base and the chair model. If you go and you zoom, just make this a bit bigger, you could see over here under the names where each component is coming from the other models that we are using. So all that I've got to go and do here is I've just got to change this to bottom and then turn my shell thickness effects on to yes, so that they pick up, because you could see I went and included the offset to make them try and match up. Realistically, this isn't going to be connected quite this way, so this might give us a little bit of errors later on. But for now, I think this is a fair assumption just to get the load transferred across. Then, because we're not using gravity, what we are going to do is we're going to just go and insert a force. And the force is going to just be where the person is sitting, and it's just going to be downwards. So all that I'm doing now is I'm just holding in the left mouse button, and then I just go click on those two over there. Alternatively, the name selections did come across, so I could have used the name selection, but I just wanted to do it this way. And then under the components, I can go and put in the Y direction, just a -1250 to approximate the 125 kilograms. Then, because this person is much like me, a chronic leaner, we're going to go and put a backwards force on the chair as well. So I'm just going to go and insert a force in the Z direction of about 200 newtons. Okay, so now we've defined our forces. The only thing left for us to define is now going to be the supports. So at the bottom over here, I'm going to go and insert some fixed supports. Just for this analysis, we could go and include some more realistic supporting conditions, and that will be fine for the topology optimization model. But in this case, I'm not going to worry about that. I'm just going to go and insert a fixed support. And then we'll go through our usual analysis settings, going to turn on large deflection and all of that. Okay, so that is how we group everything together, stick it all together within one model, and you can see there's a lot of control over how we can actually go and change everything. Then if you come to the mesh over here, everything's already meshed, so we don't actually have to do anything under these settings over here. The settings from the other models are not transferred, unfortunately, but you can see this is the mesh that we created in our other models, and it's been transferred seamlessly into this global model. So that is good enough for now. So now what I'm going to do is I'm just going to close mechanical, and then I'm going to go to the saved version, which is going to be this one. Yeah. No, sorry, the first one. Okay, so this is just a duplicate of what we've already done, and then we'll go through the normal steps, but I'd just like to go over here and use this as the starting point for the topology optimization workflow. So you can see everything's connected up the way that it was previously. We don't have to worry about the original models, conditions, and the results and all of that over there, because we've resolved it now with our new base. So then we can go and look at this model as we've created it in the previous example. Again, everything is as we expect. We've got that same contact region and everything. And now what we could see is, okay, from the previous model, because we had a harmonic analysis for the leaning backwards, and that's something we'd like to consider for the topology optimization, we cannot unfortunately just go and insert that like we did with the previous models. We have to go and include it as an additional force. That's why we put it in over there. And then we can look at our equivalent stress. And again, it's also on this back part over here. And at the moment, the bottom isn't really seeing any real stress. The problem is if we come over here to the base and we go and look at what the base is, and we go to the properties over here, we can see that this base is about 33 kilograms. So it might reduce our deflection, and it might be very strong, and we don't see any high stresses or anything like that in the base. It's going to be very, very heavy. This chair is going to be almost impossible to move around. So that's why we might want to consider the topology optimization. So the way that we do our topology optimization is we're going to just go and close this model. So we've had a look at our results. They seem to make sense. We're happy with them. So now we're going to just close this. And we're going to go and add in our topology optimization to our structure tree. So it used to be called topology optimization in the analysis systems here, but now it's actually called structural optimization. So the way that we link all of this up is we're just going to take this and drop it on the solution. So this is going to require an additional solve. You'll see now why, but then it's going to link up the model and the solution information for us. And now that we've done that, we can go back into the model. We have to access it from the furthest left one. So if I double click here, it's not going to do anything. If I do the same there, it's not going to do anything. So when we use this mechanical model for the combined model, we just have to go back and double click over there, and it's going to open up mechanical with all of our models included. Okay, so now it went and cleared our results for us because it needs to transfer that to the topology optimization. But Fear not, because we have the saved results under a different Workbench project over here, so that'll save us a lot of time. Okay, so we've defined everything for our static structural. So now if we come to our structural optimization over here, you could see it's giving us some initial information that Ansys went and populated for us. So our design region is all blue, exclusion region. The objective is to minimize compliance. So basically compliance is just we want to basically eat away where the load path is currently not. So we're maximizing our stiffness and we are minimizing our mass. That's it. That's the way you can think of it. And then we just went and put in a constraint, a response constraint over here. But we're going to look at how we can go and manipulate all of these. So step by step, the way I work through everything, top to bottom. So let's start off with the analysis settings. Usually for most of the stuff over here, we are going to go and leave these at the default. So the penalty factor, maximum number of iterations. Usually I'd leave that unless you have run your initial step, which we have done now, and you'd like to refine it more. Then you can go and play around with these over here. Then we've got our output controls, our solver controls, but most of the stuff, just by default, you're going to want to leave it in over there. So now we could see some interesting things. We've got a manufacturing constraint region, okay? We've got a minimum member size region, and then a region of additive manufacturing overhead constraints. So these are all of the constraints, and you can see them from the context tab that we can use for our topology optimization. And as you could see, there's quite a few that are already geared towards additive manufacturing. So the additive manufacturing overhand constraint, and then we also have under our response constraints and our manufacturing constraint, like our member size and so on. So that becomes more important for our additive manufacturing. So the first thing that I need to do is when I look at this, I can see that over here, sorry, I'm just going to mute someone. Sorry about that. So over here, we could see that the design region is the entire structure, but I'm not actually interested in the top section. So all that I've got to do is come and change the design region, so the optimization region, to be the base over there. Okay, great. We've got that base in. Then under the exclusion region, by default, what it does is it goes and it selects all of our boundary conditions. And because I wasn't thinking clearly when I created my previous name selection, it did not transfer into my previously solved model. So unfortunately, I can't show you how I would apply that very quickly, but I can still show you how that will work. So within my exclusion region, I'm going to go to geometry selection. And then over here, I'm just going to select the regions that I don't want to be optimized for. So that's going to be where my wheels are going to be attached, and then where the base of the chair is going to be attached to the rest of the chair. So I'm going to select those, and those are the regions of exclusion for me. Then under the optimization option, there are a couple of other options over here. So we've got our density-based, our level set. So between these two, there's just only one big difference, and that is the algorithm that they use. So the top one uses the SIMP algorithm. So basically what it does is it uses a penalty to either turn elements on or off. And then the level set uses a level set that it creates of the actual optimization procedure and does the optimization algorithm based on that. But in this case, I'm not going to bore you with the technical details. I'm just saying that the density based is usually faster and the level set is usually produces a smoother result. Then we have the lattice optimization. Sorry, somebody is joined again. That is not on mute. Yeah, sorry, I just muted them, Laura.
Yeah.
Okay, and then we have the lattice optimization. So that's going to be for your lattice within a 3D printed part, and then shape optimization. And this is quite new. It actually goes and moves your nodes and that around in order to do the optimization. Okay, so that's the boring technicalities out of the way. Then we have our objective. So over here, under the objective, by default, it's going to bring in compliance when we attach it to a static structural. And then the formulation is program controlled. Usually we don't go and edit all of these things unless you've got multiple environments. You can go and change that over there. But in this case, I'm not too concerned. I know that I want to reduce the weight and maximize the stiffness. And then we've got our response constraint. So within the response constraints over here, look, there are other ones. So let me just quickly add in an additional one. So over here, we've got accumulated plastic strain, then we've got mass, and we have volume. So those are the ones that we've got by default. I'm just going to go and delete that one again because it's not going to impact us. And then coming back to the response constraint, here we are going to try and get our mass based off of this to be 50% of the original mass. But often what I would like to do is I don't know exactly what I want at the end, so I'll go and give it a range instead. So under my range, I'll go and I'll choose, for example, maybe 10% of the original mass to 15% of, 10% and 15%. So that gives us a little range that we'll optimize within. Then there are a couple of others, so we can change our optimization region, objective, mass constraint, volume constraint. We can go and include a global von Mises stress constraint. So that is useful, but it does take a little bit longer because it has to go and calculate. There's just more calculation steps involved. Then a displacement constraint to achieve a desired displacement on this part or maximum. Local von Mises constraint. Then we have reaction forces. So based off of our fixed supports, we can define it based off of that. So there's quite a lot. Some interesting ones that you can have a look at is, for example, the center of gravity and the moment of inertia. So while we are optimizing this, we can go and say, because this guy leans back all the time, let's put the center of mass more towards the front of this chair now, because it's still going to be a little bit heavier. And then we've got our sort of additive manufacturing constraints. So for aircraft applications, these two could be quite useful, but in our case, we're not really too worried about them. So what we'll do is, after we've set up everything, we can go and we'll just say solve. I would love to have shown you a live update of how this solves, but because it's going to take a while, we don't have time for that. So I'm going to just move on to the next phase, which is going to be the solved topology optimization model, which is going to be this one over here. So again, the same structure, just different names. And now we can go and have a look at the results for that initial setup that we did. So what it does is it actually starts off, the topology optimization starts off with all of the elements enabled. And then what it does is it identifies elements that are not actually carrying the load along the load path, and it goes and it removes them using this density-based method. So I was playing around with a couple of additional constraints over here, mainly for the member size and so on, just to see what interesting shapes I could get. But the problem is that the structural optimization does take quite some time to actually solve. So it's not ideal. It could take a couple of hours to solve, so that's a downfall. But if you do use something like Discovery for very basic analysis, though, that's almost instantaneously updated. So let's have a look at our result. So after we optimized it, very much what we would expect, it went and it ate away all of the geometry leading up to where the chair is going to be mounted. So what we can do is we can actually go and just use the slider over here to see if we kept our retained threshold at a much higher value, then that's what we would get. So we can actually keep that geometry over there. Or if we had to increase our sensitivity, then you can see how we eat away even more. So then you've got like a little hole in the front over here, and these members just become a lot thinner. So you can see that this is very coarse at the moment. The reason being is because we use quite large elements. If you do want a very fine or a very smooth result, what I would suggest is use the level set. and then you also use a very fine mesh. So I'm wondering if it will be able to display it for us. No, unfortunately not. It does the exact same thing. Okay, so once we've got our topology density that we actually want, I'm just going to put that back at 0.5. So this is basically, it's just indicating what it absolutely has to keep, what's marginal, and what it has to remove when we go and adjust that slider. Then what we would typically do is we want to actually, we can't just use this result. Okay, we've got our picture of what our optimized geometry looks like somewhat. But now we can't actually go and use this for anything until we go and do a little bit of post-processing on it. So the way that we go about doing this is we would actually go over here to topology density, right click, and then we can go and say export as an STL or as a smoothed STL file. So let me go and export as an STL, and I'll just stick it on the desktop and say Topology Optimization version 1. And then let's go and export the STL, cancel. And then let's go and export the smoothed STL file. And let's just make that version 2. Okay, so that's all that we've got to do over here. If we go back into the workbench, there are a couple of workflows that we can use. So I just want to highlight them for you, but I myself do not like to do it this way. I'll use it as a starting point, but then I'll go and refine everything. So once we've gone and we've done this, we can go and transfer to a design validation system with the geometry. So what that will do is it'll allow us to edit the geometry when we do our validation study, or we can go and just do transfer to validation system model. And what that will do is that smoothed STL that we created, it'll export that and use that for our validation study. But I like to go and clean up my geometry a lot more, so I'll typically use this. But because of the way that everything's set up, I'm going to use the previous workflow where I have this combined model over here, and then I'm going to just go and edit it like that. So now what we'll do is we'll go into SpaceClaim. So this is our geometry cleanup part of the process. So we've gone through our initial static structural simulation. We went and did our topology optimization with very basic constraints and objectives, but it's just to highlight the workflow. If you want to go and manipulate any of the other objectives, you're more than welcome to do so. Then I'm going to go and say open and just go to my desktop and say all supported files on desktop. And then let's go and open, sorry, that one and that one. Okay, so we've got the version 1 over here. So you can see these are the facets that we get out. Not ideal. The one nice thing is it did go and maintain quite a nice circular shape in the center there, but you could see they're all different directions. This is not something we would like to work with. Whereas if we go and look at our smooth SCL, well, that looks much better already from the start. But when we get going, we don't really want to use all of this, because what mechanical is going to do is it's going to take each one of these as an element, and it's going to have to use these as the nodes for the meshing strategy. So we can do that. We could go here and say convert to solid. But I do not want to do that just yet. I first want to use the dedicated tools that Ansys has to go and smooth this out. So I'm just going to go and let's go Control A and then Control C, Control V. So now I've got a copy. So let's start off by going to the facets tool over here. And my favorite tool, I think, is probably this one over here, the shrink wrap. So what this allows us to do is it allows us to effectively shrink wrap this geometry and then go and smooth it or eliminate, like for example, these small holes and that type of thing. So what I'm going to do is I'm going to just say, let's make this very fine and put it at 5, and then let's go and say keep original bodies. There are some additional features over here, so we can change our max gap and preserve features, but because this is all very curvy in any case, we don't need to worry about that too much. Then we could select this geometry and say, okay, let's go and shrink wrap it. Okay, so now that we've done that, we've got the shrink wrap over here, and it went and it eliminated that hole over there. It just wrapped around it, and we've got a fairly consistent sizing around all of this over here. Now, what you can do is there are some additional tools over here. We don't need to use any of the modify tools at the moment, but something that is quite nice is the smooth. So if we click on smooth and we click on this shrink wrap over there, now if you come and look at what's happening over here, you can see all of the sharp edges and everything like that. If we click on smooth it out, smooth, 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 you can see how we are slowly actually just removing all of those sharp corners. Something that I don't like that I can see is probably going to give us a problem is going to be this over here. So all that I do is I go and just delete those. And now we've got a tool to fill up that gap. So go to the holes and say, cool, fill it up. And then I'm going to go back to smoothing this thing out again. So we could go there and then smooth it a couple more times. So we've got quite a smooth shape now. And then if we want to, we can always reduce it. So if we select the shrink wrap and we say reduce, what it will do is it'll just make these triangles bigger. So there's quite a lot of tools available, but yeah, I'm not gonna worry too much about that. I'm just gonna go and just smooth it out one more time just to make sure. Okay, perfect. So this is the shape that we are going to use. But now something that I do not want is going to be this obscure hole that we've created in the center there. So the way that I go about this is I'm just going to go and change this smart select to say through. It can actually still be smart, but it has to just be through. And then I'm just going to go and draw a square around this over here. So what it does is it selects the objects on both sides, and I'm just going to delete them. And then I'm going to use that hole fill tool basically to fix them up one by one. And then now we've completely eliminated that hole in the center. Okay, so let's say we are happy with this geometry that we've got over here now. What we can do is we can go and select the shrink wrap, and we could go and say convert to solid, and we'll just merge the faces in this case. So what it's going to do now is it's just going to go and take this faceted body and convert it into a solid for us. So once we have our solid, we can take it back into our validation system, and then we could go and do our additional analyses. So something that often happens is when we go and create this into a solid, we have all of these lots of little tessellated surfaces. So that is the first way. So I'm just going to undo that. And now another really great tool that we have is this auto skin feature. If I click on this and I say auto skin, what it's going to do is it's going to go and create a really smooth geometry for us. So you'll see now that looks much better. Okay, so now we've got all of that included over here. So now the last thing that we have to do is we have to go cut out all of the holes again where they were originally. And that is as simple as going over here and saying assembly, add a file, and then we just have to go to this geometry, and it is the cutouts. And what I did is I pre-created all of these cutouts for where the holes are going to be. And now all that we have to do is we just have to go into design, split this body by that over there, and we delete that. Then we could split it by that one, and then just delete that, and then split it by that one, and delete that, split it by that one. And there we go. So if I hide all of those, there we have all of our holes cut out very quickly, very easily for our analysis. So that is the typical workflow. You might get a little bit stuck between the facets and the auto skin feature. There are more tools available, but we don't really have time to go through those today. So I hope that that just gives you indication as to the workflow. And now what we can do is we can go about actually transferring this to a new model. So the way that we would usually do this is, let's go, I would, for example, just go and suppress all of these. express with physics. And now we're only going to transfer this into our actual model. So I can close this and let's just say yes. Okay. Okay. So we've done our structural optimization over there. So now what I'm going to do is I'm going to go and duplicate this again, so that we can transfer all of the relevant boundary conditions and everything from our chair. So this is going to be our chair model again. We're going to link it up to this model again, and then we just have to go over to the final static structural validation system. So this is the way I would typically do it if I was working with this model. Otherwise, I would most likely go and use the validation transfer to validation with geometry, and that keeps all of the original boundary conditions. Oh, okay. So what it's doing is I accidentally selected all three for the duplicate function. So it went and it duplicates that over there. So this should still be okay. What I'm going to do is I'm just going to come over here to the geometry and then just go and insert our optimized geometry. So our very crude topology optimization study that we ran, we're just going to go and insert that geometry over here for our topology optimization study. So I think that effectively, maybe I need to just skip a little bit ahead because I see that we are running out of time a little bit. So I'll basically repeat the same process as what I did for the previous study, except now it will just be for the optimized topology. So with that being done, I think let me move on to the last section, which is then going to be the sorry. Just have to open this one so I can demonstrate the next part, but let's continue so I can just show you the actual model that we set up and the results. So what we have to do is we just have to go and apply a results and boundary conditions to the original locations of the original geometry. So the chair setup, great. We don't have to worry about that because of this workflow, but we do have to go and apply our fixed supports to the bottom of the optimized topology. So here we have our new, very interesting, almost drone-like base structure for the chair. And we can look at our mesh. So in this case, what I did is I went and I put a very, very coarse mesh on here. The reason being is we would like to look at a little bit of the sub-modeling process for this. So I went and applied a very coarse mesh over there, and then we could solve it like that. So the other things that I changed, so we just have that same contact region that we had in the previous one over there. So this is probably going to give us a little bit of issues with the stress because the contact face is just facing the wrong direction. So there's going to be a lot of excessive penetration over there, but let's not worry about that too much. And then we've got our optimized base brought in and aluminium alloy and all of that. Okay, so if we go and have a look at our equivalent stress, you could see that we are getting quite high stress regions now. Again, it's going to be over here at the bottom of the structure, and then the base structure over here, we don't have too high of a stress, maybe just on the inside over there. So we could see that this is a possible potential area for mesh refinement. Another thing that I just want to point out is I used a remote displacement instead of a fixed support. So what that allows us to do is it allows us to give these a deformable behavior. So relative to the coordinate system that's been defined, which is based over there. these holes and stuff like that are actually allowed to deform. So we constraining the X, Y, and Z displacements of them, but they are allowed to deform. So they're not going to keep the exact original shape that they had. They will be bending and moving a little bit. So that's effectively what we've got. And this thing is bending forward quite a bit. So once we've done all of our boundary conditions and everything like that, we would want to go and transfer this into a
which we need to
submodel.
Which we need to look at that is
Yeah.
Yeah, so I think I'll if
Okay. So let me just close this, and then I can just quickly show you the submodeling procedure. Okay. So this is the full model that we've done our solved static structural analysis on. So what we would have to do is typically we would want to go and create a submodel of a region within here. The way that we could do that is we can actually just take all of the geometry that we've got between these two and combine it into a new static structural analysis. So we'll start off by dragging a static structural analysis across over here. And then we can go and select under the geometry. So when we do our submodeling, one of the key things that you need to try and keep in mind is we want to take our cut boundary constraint. So when we import our model and we apply the displacements to the nodes, then the cut boundary constraint is going to have high stresses because we're not capturing the stiffness of the entire structure. We're only going to be capturing the stiffness of the structure that we have included. And then it's going to be over here, sorry. So we are going to have very high stresses within those regions. So that's something to keep in mind. So what we typically will do is we will go and manipulate that in such a way that we have the cut boundary constraint further away from the actual region of interest. So I'll show you exactly how we do that. So I think it is this one over here. So let's open up that one. So this is going to be the full chair model. All that I've done is I've removed all of these bottom components over here because we don't need that. And then I'm going to go and under assembly, go and add in the optimized base that we have looked at. I think that one. And then I'll go and include that over there. So now when we are looking at our submodeling, we don't need all of this detail over here. So the first thing I'm going to do is I'm going to go and just select over there, drop a plane in. And then if I go to the side view, I'm going to just go and move this plane up a little bit. And then I'm going to go and split this body by the plane. And then everything above the plane, I don't need for the submodel. So the only reason that I'm doing this, typically you would want to refine your submodel a little bit more to the region of interest. So maybe a cut around there and then a cut around there to see the stresses within that region. But I just would like to show you how we can use a shell model in the global model and then a solid for the submodel. So we can actually transfer the data between those two. Okay, so now we've got that first part, and now I'm going to go and cut out all of those supports. So I just want to view that over there. And then, as I mentioned, we're going to have two separate cutouts. So the first thing is I'm going to select sketch mode. Then I'm just going to go and create a circle over there. Pop it in, and then create another circle, maybe over there. So now what we're going to be doing is we're going to be looking at this region for our submodel. Now, if I go to the 3D view, what I've got to do is I've just got to take that edge, and I'm just going to pull them, no merge in this direction, and then just take them through over there. Okay, great, that's what I wanted. Then we just have to split this body by the outer circle. So we've got all of these separate instances. this I can delete. And then just delete all of these. So that's where the cut boundary constraint is going to be. For some reason, that one is not deleting. No, not to worry. That is here. Okay, and now we've got that base over there. And now we're going to just go and apply our additional cuts. Maybe this one, I'm actually just going to go and select that and then merge and just drag that in a bit more. Let's say that's the actual region that we want. And then we could go and say split this body by that surface over there. And then this body, we just have to suppress for physics. And that will also then be suppressed for physics. And that's already suppressed. So hide all suppressed. Okay, and this is our submodel. So often what you can do is you can go and create a shared topology between these parts over here. I did not do that just for the simple reason that I wanted to have very big elements on this body and then very small elements on that body. So this is what we've got over here. Now all that I've got to do is I've just got to select this one. So that's 2 millimeters. So I'm going to go and pull this one as well in both directions and just make it 2. And there we go. So now this is a solid that's going to be receiving a shell's displacement information. Then again, I want to just keep this here so we can have that contact region. And then we've got our submodel defined. Great. So now that we've got all of this transferred, we can go into the model itself. What I like to do is I take the solution and then you'll drag and drop it onto the setup over there. But let's just go into the model first so that we can just go and check all of our conditions. And then after that, we'll quickly go and update everything. And then I'll take you to the final solved model where we have all of the results ready for our analysis. Okay, so it's just bringing everything in. Okay, so again, the nice thing is all of these over here, I just have to go and select that. These are all going to be our aluminum alloy. And then these ones too will also just be alloy. Then we've got our materials defined, coordinate systems connections. So again, it goes and it creates a connection between those two bodies over there. And then between those two bodies over there. For this one, I just have to go and make sure between, suppress that one, and then go and insert a manual contact region. So what I'm doing here is I'm just going to select this to be the contact, and then select that to be the target. And then because we've got a mid surface over there, we just have to change that again so they are facing each other, activate the shell thickness effect, and that is ready. Then for the mesh, what I typically would do is I'll go over here to the mesh and then insert over here a sizing. So this is the body of interest. So I actually want to see what the stress is within that region over there. So over here, I'll go maybe put in like a 5 millimeter mesh sizing. Then over here, I'll go and insert maybe a 10 millimeter mesh sizing. And then on these bodies over here, I'll go and insert another 5mm mesh sizing. We can then go and generate the mesh for this. And that's effectively all that we need at this point. So now we can see we've got a very coarse mesh around there. The bonded contact will keep everything in check. So now before you could see over here, we don't have our constraints pulled in automatically because we haven't linked up the system. So something very important that I'm going to just show you now is when we link up everything, the key thing that we have to do is we have to take the solution, drop it onto the setup, and we have to access the model from the setup. If we try and access the model from the model, so cell V4, then it's not going to pick up the solution information from the previous model for the submodel. So that's very important to take note of when you are doing your submodeling. And now you could see straight away automatically it went and it brought in the submodeling branch. So all that we have to do is we have to go and insert a cut boundary constraint. So you could see there's a cut boundary remote force, cut boundary constraint over here, remote constraints, and a body temperature. Because ours is directly linked up, we just have to go and put in the cut boundary constraint. So I'm going to have two. The reason being is the first one is going to be our shell to solid. So if we go and select it up there, and then over here, we just have to go and say shell to solid. And then for the second one is going to be all of these other cuts that we made. So I go and insert another cut boundary constraint. And now what I'm going to do is I'm just going to select all of these faces. Okay, and now something that's quite cool that I'd like to show you. When you are doing submodeling, sometimes there might be a little bit of an error if the models aren't exactly aligned. So the way that we would ideally do this is just turn on show source points. So what it's done now is it's taking all of the source points from the global model. So you can see basically the chairs over there, and it's just showing you where this is in relation to that. So we can go and import these loads now. And here are the cut boundary constraints. So you can see it's going and applying to the top and the bottom surface of the solid due to the shell to solid submodeling. And then again, for this one, because we're showing all of the points, I'm just going to turn that off. We could see that it's importing all of these loads over here on the different feet of the structure. And there you have it. That's your typical submodeling workflow. So now we could just go and have a quick look at the results. So one thing to keep in mind is in the central region that we were modeling, we are unfortunately not capturing the realistic connection. So what you will see is from this model, we're going to have excessively high stresses, but it's because we are not modeling how this would be bolted or how it would be connected. We're basically sticking everything together, and with that shell thickness effect, it's actually pushing everything out a little bit, so we get these very high stresses. So again, you can see over here, these are the constraints we brought in with the different models. In this case, you just have to go and apply standard Earth gravity again, just to it. If there are, say now, for example, there was a load on this face, we would have to go and apply that again under the submodel over here. So any external loads we would have to apply again. And then we can go and look. So the first thing I'd like to show you is this is the global model. So you could see when we look at this, because in these corners over here, we are not capturing the stiffness of what used to be there. We have got these excessively high stresses up to 16,000 MPa. So that's why we use the second cut, because then if we look at it, so it goes down to 1,000. So it's still very, very high within this region. So as I mentioned, it's because we're sticking everything together over here. This is basically taking none of the load, and everything's been transferred onto the space structure over here. So we will have to go and address that in the design phase again. But you can see now we can get a much more high fidelity result than compared to the previous one. Ideally, what you would like to do now is you would take the total deformation and we would chuck some probes, for example, over there, over there, over there, over there, and over there, and just all over on this model. And then what we would do is we would take all of these and we'd go compare it back with our initial model over here and just make sure that the probe results look like they represent one another. So that is it. So that is the typical workflow for a sub-modeling process. So as you can see, this design with our chronic rocker or our chronic leaner, we are going to have to go and reevaluate this. And as I mentioned, it's an iterative process. So we're going to have to go back, do the topology optimization again, fix it up, maybe look at how this thing is actually bolted on, and then we can go through this workflow again. Okay, so thank you, everyone. That is it for the webinar from my side. So what we can do now is if there are any questions in the chat, we can address those. And I believe that Laura will most likely be uploading the recording somewhere for us to access in the future.
Yes, that's correct. Thanks, Josie. And thanks for everybody attending the session. As Josie said, is there any questions that we can address now? Thanks, well presented. I think, Josie, what we will do, maybe we'll just do a session. I'll be sending the recording out, as you said, to everybody afterwards.